are you sharing the PowerPoint?
I should be.
Yes, you are. Okay. All right.
All right. So, final review to kind of go over everything one last time, and hopefully it's beneficial. So,
Oh,
to start, basic engineering principles. A sketch is a quick free-handed drawing intended to provide a starting point to revisit an idea later. These are usually not very clean, as you can see in the picture provided. They just get the general idea down. A pictorial drawing is a 2D illustration that represents a 3D object showing its height, width, and depth in a single view. There are two types of pictorial drawings that are relevant to this class: axonometric drawings and oblique drawings. An axonometric view is a type of pictorial drawing that shows an object in 3 dimensions on a 2D surface, but without perspective foreshortening. There are three types of these views. The one that we probably know best is isometric, and the angles between all three axes on an isometric drawing are equal, meaning that they're 120 degrees each. On a dimetric, excuse me, on a dimetric view, the angles between two of the three axes are equal. So, like for instance, in the picture provided, two of the angles between the drawings are 131 degrees, while the third one is 97. And then a trimetric view, all the angles between all of the axes are unequal. Like for instance, the 105, 120, and what I'm assuming should be 135. So it's kind of the same as triangles, but yeah.
Wait, so sorry to
Oblique
interrupt. So,
sketches, pictorial sketches which represent the object's front face with its
okay.
true dimensions and add depth by drawing receding lines at an angle, which can be full or reduced in length. So the main reason why you would want to use an oblique sketch is to capture detail on the front face, because an oblique sketch has the front face in the plane of the paper, so it's easier to see in true dimensions, whereas while an isometric would have it at an angle, which makes it harder to see. And so rotation about an axis. So basically the entire principle about rotation about an axis is the edge located on the axis that is being rotated about does not move. So like for instance, in the pictures here that I have from SolidWorks, the bottom left axis is highlighted to show that when I rotated it about that axis, it didn't move, it's still on that axis. And then the point of the model that is the point of the model that is correlated to the origin will not move from the origin as long as the model is continued to be rotated about one of your three major axes: x equals 0, y equals 0, or z equals 0. Santana, this is you.
okay. So, all right. So now we're going to be going over engineering design and the engineering design process. So, engineering design is a decision-making process, uh, um, in which the basic sciences, mathematics, and engineering sciences are applied to convert resources optimally and to meet a stated objective. Basically, what it's trying to say is just like it's just a process to and to apply all the concepts that we're going to learn and are learning. So and to create the design product. So yeah. So this slide will go over some of the general aspects of our design process. So we have recognition of need. Basically, we are given a problem definition. We are like giving some of the requirements. Conceptualization is kind of drafting. Concept selection is like self-explanatory. Preliminary design is like a basic design of our idea. Detailed design gets more sophisticated and will eventually spit out the final product. And then verification and validation is just submitting your design and seeing if it meets your requirements. Okay, so as stated before, recognition of need. There's a problem. So like for an example, right? Our design project, for an example, lack of accessible playgrounds. So that is the problem that we are given. And then our next ones. So again, Finding a problem to solve is a lot is comes from all different forms, right? It can come from like formal requests or informal requests, unsolicited proposals, assignments from supervisors, adaptations to make pursuant to new legislation needs that could develop in market. So basically, like if there is something new that needs to be done, or or like something that needs to be improved, that's basically it. It can even come like even from your sleep. That does happen for a lot of people. But like this is just like the general idea of where all of your problems are going to come from. So your problem definition are some of the requirements that are given to you, so that to do your as they're basically like restrictions for your design and for your ideas. So and you must have a full understanding of all your problems and specifications. You cannot have one or the other. You need to have all of them to be applied in some way. That is the lead to a great design, is it must have all of those specifications. So over here on this slide, we have the different types of requirements over here: functional performance, human factors, physical requirements, reliability, life cycle requirements, resource cost, and manufacturing requirements. So like so like these are just some types. There could be more that but like these are like the general these are like the general idea of what we're going at. So for conceptualization is concept conceptualization is just it's just like trying to lay out some basic ideas of what your design is going to be. So like essentially it's like brainstorming, right? You have your 6-3-5 method, as we went over in lecture. So, and then over here is basically like an example of what some machines will be doing, or some devices with their functionalities, and we would just select based on all these and which ones would meet the requirements, and also which one that is more suitable for us. Now, for concept selection, a decision matrix will be used. So if you remember how to do your decision matrix, this you will have to review on that. But basically, you're going to be putting each requirement in a certain weight out of 100, and then you're going to rate them, and you're going to rate them out of each, and you're going to have a weight and unweighted. And I'm not going to get into the process like super quickly, because I'm trying not to be broad, and also I'm trying not to rush, but essentially, like this is how you're going to be choosing your device, and how it's going to be how it's going to function based on your requirements. Excuse me, I need to take a swig. Okay, so preliminary design is just our basic concept drawings. We're just laying out like a basic foundation of what our idea is going to be. So then, from detailed designs will eventually just become. It's going to have more sophisticated machinery, more parts, more detail. And so with that more detail, then that will allow us to continue with this continue designing what we're trying to do. So you see here is like you're going to be your design is going to be more sophisticated and become more complex as you keep drawing and drawing. So. All right. So when it comes to detailed designs, this is when you want to be very specific and very critical of what your design is going to be. So like make sure you have your dimensions and interfaces, your materials, your parameters, your quality standards, your testing, your design life. You basically want to take all of those into consideration to make sure that your product is the best that it can be. And then verification validation is just basically submitting the project and ensuring that this has the right requirements. It meets all the marks that you were given. So like, did you design the product right, and did you design the right product? So okay.
Alright, so now we're going to move on to solid modeling. So a solid model is a mathematical representation of a physical object that includes the surfaces and the interior material. The solid model is a computer-based simulation that provides a visual display of an object as if it existed in 3 dimensions, provides an accurate description of part geometry, and it's used in many phases of the design process. Usually they're created with specialized software, such as SolidWorks, as we've used in this class. Some others include Autodesk Fusion, Inventor, AutoCAD, and others. However, these solid models must still be built with sound modeling practices. So, moving on to solid modeling parts. Parts are made up of features. Features are the distinctive geometric shapes that form the part, and some features include protrusions, holes, chamfers, fillets, and rounds, which I'll get into just after this. But the first feature created is known as the base feature. So everything in a solid model builds off of the base feature. So protrusions, assuming that the rectangular prism there at the bottom is your base feature, the cube and cylinder are protrusions off of that because they extend off of the part. So, instances are assemblies. We'll get there. So basically, a protrusion is anything that's like sticks off of your base model as seen with the cube and the cylinder. However, so just want to clarify this because they sound very similar. Extrusion versus protrusion. An extrusion is the process of extending a 2D sketch into a 3D object, but a protrusion is the feature that creates a raised or elevated part. So basically, extrusions cause protrusions, or can cause protrusions, but just wanted to clarify that because they sound similar. Holes. There are 6 different types of holes. You have your spot face holes, which have a very small counter bore on them, usually used for hex nuts, I believe. Your through hole, which, as it says, goes all the way through. Threaded hole, which contains threads inside of it. Blind hole, which is like it's a hole of a certain diameter that goes down a certain amount but doesn't go all the way through. Countersunk hole, which is the angled one, and I like to think of it like it's also called countersink. It's like how a sink sends water down the drain. A countersunk hole would also send water down the hole if water was poured in there because it's angled. And then counterboard, that has a diameter of a wider diameter that goes down a certain extent, and then a smaller diameter continues it the rest of the way through, kind of creating a little ledge. Chamfers versus fillets. A fillet is rounded while a chamfer is like at an angle. So like as you can see in the picture here, these are the same model. However, the fillets make it look smooth and rounded, whereas the chamfers are a little bit more abrupt and make it at usually 45, but whatever angle you want. And fillets versus rounds. So a fillet is on the interior corner of a shape. So like for instance, on the inside of that L is a fillet, while rounds are on the exterior side of the shape. Parameters. So parameters are an attribute of a feature that can be modified. Some parameters include dimensions, geometric relationships, which I believe we'll get into next, and parametric modeling uses parameters to define a model. The key thing about parameters, though, is that a parameter can be changed, and the model and all associated assemblies and drawings will be updated to reflect the change. All right, so getting into those geometric relations that we were talking about, the 6 main ones that you need to remember for lines is horizontal, which makes a line horizontal, and likewise vertical, which makes lines vertical. There's also coincident, which causes 2 lines to fall on the same line. So like for instance, in that picture, you have the 2 separate lines that were made coincident, so now they form a single line, say fall on the same line. Midpoint, which will place a line at the midpoint of another line. So like for instance, in that picture, the line that is currently being drawn is located at the midpoint of that horizontal line. Perpendicular will make two lines at a 90-degree angle to one another. Tangent will make a line, basically make it smooth and make it at the same angle and slope as as a curve before it. And then two that I couldn't find pictures for are equal, which makes two lines have the same length, and fix, which makes a line not be able to move. Kind of similar to how you have fix and floats in SolidWorks for assemblies. You can fix a line to keep it where it is. Between circles, so there's tangent, which causes, and tangent can also be between a circle and a line, but it causes circles to intersect at one point. Concentric causes circles to possess the same center point. Equal causes circles to have the same radius. Co-radial causes circles to become the same size and have the same center point. So basically, co-radial is if you had equal and concentric together. That's what co-radial is. And then fix, like it was on the lines, causes a circle to become fixed in place and not be able to move. So next we're moving on to methods of extrusion. You have the good old boss, where you take a 2D sketch, extend it by a certain amount, and now you have a 3D object. Revolution, where you you have a sketch of an object and an axis that can or not necessarily be fixed to one another. To answer your question, yeah, the slides will be posted, and this is also being recorded, and the video will be put out. So as I was saying, so like for instance, here on the right side, you have your rectangular sketch and the blue axis that is in the middle. And so when you revolve it, it'll keep that rectangular shape all the way around the axis, and therefore you have a 3D solid. In this case, it's a cylinder with a hole in it. Sweep. So sweep is you have a profile, which in this case would be the oval or ellipsoid shapes. And then you also have a path, which is demonstrated by the line. And the sweep will take that profile, which is the oval, and basically extrude it along your path, and you'll have a 3D object. So like for instance, in this picture, you have the oval as your profile, and the line kind of makes a U shape. And then when you extrude it, you'll have a U that has a cross section of that oval the entire way. Thin. So thin is kind of like a boss, except it can be made to really small, or it can be made to really small dimensions for a certain extent. I don't know if that made sense, but basically you would use a thin for smaller parts on an extrusion for a certain distance. Loft. So loft, you have however many different sketches you want, and basically by using the loft, it'll put them all together and it'll create the solid between each of your sketches and make it smoothly transition between them. So like for instance, here you have sketches 1 and 3, which are kind of your shorter semicircle, and then sketch 2 has a larger semicircle. So the loft will take the left semicircle, extend it out to the second one, and then bring it back into the third. So now we're going to move on to creating features. You have your shell feature, which takes a solid and basically empties it except for a certain distance. So like for instance, in this picture, it'll take out the interior of the solid, but it'll leave a 1/8 of an inch border around it, and that'll shell it. Linear pattern can be used to replicate features. So like for instance here, you can take rather than making 18 different holes, you can just make one of the holes and then create a linear pattern that is 6 instances over and 3 instances down, and it'll create this pattern. Likely you have circular pattern, where same thing, rather than making all 8 of these holes, you just have to make one, and then around a plane or an axis, you can basically revolve the object around for a certain number of instances, and it'll create it. Rib is used for support structure, so it's made using lines. And basically, to put this simply, it's used mostly for support structures, as I think I just said. But yeah, so it's made from lines. You just click on the line, it'll ask you what width do you want, give it the width, and then it'll create it. Mirrors. So if you have a symmetrical part, you only have to make one side of it, and then you could use the mirror function and just have it mirrored to the other side, and it'll make the identical part. Cynthia, back to you.
Sorry, my mic was muted.
Yeah, no worries.
Okay. All right. So now we're gonna go over engineering drawings. So the basics on engineering drawings is just how are you going to visually represent a part that you have just created. So if you remember how our lecture goes over some this method of hold on, I just had a brain fart. Excuse me. If you remember in lecture, we went over a method known as the glass box method. It's just another way of visualizing how the part is going to look like. But the essential part of it is just how you're going to let other people see what you are rendering or what you are creating. So stated before, the glass box method is a very great way of visualizing your part when it's being projected. So there is six. So there is six different views that we want to take into consideration here: front, right, back, left, top, and bottom. So if you put all these together, these will render a 3D shape that we are trying to use. But most of the time, we are going to be using front, top, and right. But also sometimes the bottom if it's a bit complex. This is like the more general idea. You're going to be putting a cube inside. You're going to be putting a cube outside of the part, and basically where you're looking at in the cube is basically your projection. All right. So what is the difference between first and third angle projection? So third angle projection is what we're going to be using primarily the most. So third angle projection is going to be front, top, and right, while first angle projection is going to be front, top, and left. Now, first angle projection is used in Asia and also Europe. Third angle is mostly used here in the U.S. So, all right. So then again, here's our first angle projection. We have our front. We have our front, top. We have our front, top, bottom, left. But then again, we only use the front view, top view, and any side and the side views. But this is just this is just our way of doing it. So this is first angle projection right here, and then our third angle projection. Okay, now section views. Basically, what is going on is that you're taking a plane and you're cutting it by some line. So on these few images, you can see that section A you're cutting it from the circle horizontally, and then section B you're cutting it vertically. Now, what do these arrows mean? Well, the arrows is basically where you're going to be looking at from the section view. So if these two arrows in section A are pointing that way, so that means you're going to be facing the wall of the part. But if if section A is the arrows are pointing in the opposite direction, you're just only going to be seeing the area that's cut and no wall. So offset section views. So instead of just cutting on one area, you're cutting by a line. So like you're essentially cutting into multiple areas. Then again, like you're also using your view arrows to signify that we're going to be looking at it from this direction. Now, as you can see, that some of these that there are lines going through these holes is because that they have because they have diameters. So anything that had so any hole or any slot that's going to be used here, there is always going to be a center line to signify that that this has some radial component to it. All right, so half section views is kind of similar to offset section views, except that you're not cutting all the way through. You're only cutting through a portion of the object. So in this example over here, you could see that it's only cutting through like a quarter of what we're looking at, and so the end result is just going to be the image on the bottom. So essentially, you're just only cutting it at a specific spot, and you're not cutting all the way through. All right, so auxiliary views. So in this image here, we could see that we have some kind of slope, right? When we're doing our regular projections, um, the angle of the angle or the face that's at the angle, it's not gonna have some true dimensions, because we're dimensioning when we're dimensioning a part, we want to have the images to be we want the pictures to have the correct dimensions and to not have it look kind of warped. So in order to counteract this, we have something what's called an auxiliary view. So when it comes to auxiliary views, you're basically adding another view based on the angle of what we are looking at. Again, using this picture here, right? Our auxiliary plane is this is our auxiliary plane, and so in order to view the auxiliary plane, we have to imagine that the slope plane is actually flat this time and not at an angle. I hope that made sense. Give me a second. I need a swig. Okay, broken out views. So broken out views are really similar to half section views, but instead you're only seeing a more specific part of an object. So for example, right, you have some kind of piece with some like hollow end, or like you have some connector pin inside. How are you going to view that pin on the inside? Well, you can actually like take a small area and essentially break it, and so that you could see the views on the inside. Let me see if there's anything else I need to do. Yeah. So once you're breaking, when you have this broken out view, it can eliminate hidden lines, and so that this can help in reducing clutter and hopefully provide clarity in how where this part is actually supposed to be, or how this part is supposed to be machined. For detailed views, you're just taking a certain area of a part, and you're just zooming in on it for more clarity. This can help when you have such a large assembly, or maybe a part with a very small like protrusion, and you just want to make it clear that, oh yeah, this is the part that we're trying to look at here, and then like this is how it's going to be done.
Right, so now we're going to move into assemblies. So an assembly is a virtual model that combines individual parts into a single complete system or product. A component is an object or a part that makes up the system. An instance is a copy of a single component within an assembly. So like for instance, if you have 40 instances of the same screw in an assembly, you would have 40 instances. Wow, that was circular reasoning. Okay. Uh, so subassemblies are groupings of components that serve a single purpose. So like for instance, going back to my bolt example, a bolt, a nut, and a washer would be a subassembly because they serve the single purpose of helping fasten something. And then associativity is a dynamic link between different parts of a model, ensuring that a change in one element automatically updates related elements like drawings, and in this case, assemblies. So like if you have a part and like let's say you change the length from 1 meter to 2 meters on it, it'll update automatically every other place that that specific component is featured. So it just makes it easier. So moving on to assembly constraints, which are also known as mates. These mates are used to maintain dimensional or geometric relationships between instances. Many of these mates are similar to solid model geometric relationships when we're still in the part stage. So you have coincident, which causes two components to fall on a line to one another. Parallel, which causes two instances to run parallel to each other. In the opposite way, you have perpendicular, which causes two components to line up at a 90-degree angle. There's concentric, which causes an object of, or two objects of diameter to share the same center point. So, like for instance, a pin and a hole. You could use concentric to move them on the same center point, so they'll go in and out of each other. You have your lock mate, which prevents movement similar to fix in the geometric relationships. You also have a distance mate, which causes two parts to maintain a certain distance from one another, and an angle mate, which causes two assemblies to maintain a specific angle. So, like for instance, if you did the CSWA, or the sample CSWA, on the assembly question when you were supposed to have certain angles between the two components, this is the mate you would use to make that happen because it would move it automatically to match that. So degrees of freedom are very important in assemblies. Degrees of freedom are the number of independent ways in which a component can move. And with no constraints, every single object has 6 degrees of freedom. It can move or translate about the x-axis. So in this case, I'm going to say left and right. Translate about the y-axis up and down. Translate about the z-axis, so forward and backwards. But it can also rotate about the x-axis, which is the object's pitch. Rotate about the y-axis, which is the yaw. And rotate about the z-axis, which is the roll. So we use these mates in order to make sure that they don't move when we don't want them to.
All right, did I unmute properly this time?
Yes.
Okay, all right. All right, so we're now going to go over tolerancing and dimensioning. Let's first go through dimensioning first. So that should be like a general guideline. So when it comes to dimensioning, we're going to have some common metrics or common units. SI, we should be very familiar with this as it's being used a lot. So like millimeters or meters, kilometers, so on and so forth. And then we have our U.S. customary units, our freedom units, our inch and pounds. Both of these units will be used in a lot of drawings, and sometimes they could be used at the same time. So just make sure of that. So we have some terminology that we need to make sure of. So we have arrowhead. So our arrowhead is basically our you see those green arrows. Those are basically pointing to where the dimensions are going to be. Our dimension line, which are the green arrows pointing outward. So our arrowhead is pointing inward, but our dimension line is pointing outward. So it basically states like where the dimension starts and where it's going to end. Extension lines. We use extension lines when we usually don't have our dimensions inside the part. So we usually have an extension line so that the dimension can be seen, and then also where the limits of and also where the dimensions are going to be lined up as. And then our leaders. So sometimes we can't have our extension lines, and some more common examples are like holes or some slots. The radius will actually be extended outward and not have dimension lines, but instead have a line and an arrow pointing to the specified part or feature. All right, so when you're dimensioning arcs, we usually use the diameter symbol, which is like a circle with a line across it. It's mostly just used in perfect circles or ellipses, but when you are working with stuff like fillets or rounds or basically anything but a perfect circle, it's best to use radius instead because having the diameter of something when it's not perfectly a circle is a little bit redundant. I should have put more pictures in here. So for dimensioning, there are some rules that you have to take into consideration. The final product must be shown. So like your isometric view must be in your drawings. All lines and dimensions must be clear. So like don't have like a bunch of like dimensions scattered around all over the place. You kind of have to want them in like a strict order. It's like equally distribute your dimensions and don't have all your dimensions in a singular view. Because if you have like you say you have a cube, right? And the front view is saying like okay, this is like 10 centimeters. Then on the side, it's also going to be 10 centimeters. But if you keep putting 10 centimeters over and over and over again, that's not going to be right. So it's best like when you have your cube, you're just going to say 10 centimeters for the front, or the width, 10 centimeters for the height, and 5 centimeters for the 5 centimeters for the depth. That's it. You don't have to like say like, oh, this corner, oh, this edge is 5 centimeters. This one is like, if you think that this dimension is obvious, then then it means that it is obvious. So just don't do that. So again, like no repeated or messy dimensions. This can avoid redundancy, so that like when people see your drawing, they're not going to be confused. And only dimension solid lines. If you're dimensioning hidden lines, that's also kind of messy. If you're going to be dimensioning hidden lines, just use the section view. Do not just don't in general just don't use dimensioning for hidden lines. So there's a couple types of dimensioning techniques that we were shown. So baseline is one that we have to excuse me, I just had another brain fart. Baseline dimensioning is one technique that we can use. So all dimensions are starting from a face or feature. So if you look at the baseline dimensioning picture that I have, you're starting at some kind of face or edge, and you're just working down from your dimensions. So you can see like this one here says 4 from for the entire length of this object, and then from the top slot to the bottom, that's 3.29, and then the circle over here or the hole is 3.01, so on and so forth. Now with chain dimensioning, your first dimension starts from your face or feature, but it actually builds up all the previous dimensions. So in this picture, right? I'm sorry if it's a little hard to see, but this one says like from the large square is 1.5. The next one, the smaller one is let's say 0.75, and then it goes on, and then it goes on and on. Contour dimensioning is just placing your dimensions in proper views. So like it's not really baseline nor chain. You're just only dimensioning the ones that are important. So okay, tolerancing. Why do we do tolerances? Well, we can't manufacture everything perfectly. There's always going to be some imperfections because if we try to always make everything perfect, there's always going to be a bunch of quality checks and everything has to be perfect, or else you're just going to scrap everything. So it's essentially a waste of resources and also a waste of money.
I have a question.
Please put it in the chat.
It's real quick. Like, did we just start, or like, have you been there, like doing it for like a minute?
No, we've been at it for over 45 minutes, dog.
Oh,
Yeah,
for shit.
we're almost 40 minutes into this thing. When we're done, I'm recording it all right now. I'll put the slideshow on the general channel, and then I'll also post the video as well.
For sure. Thank you.
Yes,
Yep.
sir, Poppy. Thank
Yeah, please remain quiet. You can put your questions in the chat. So yeah, uh, where was I again? Oh yeah, so basics on tolerances. We can't have everything perfect because it's a waste of resources and a waste of money. So tolerances is a great way to have some kind of leniency with some imperfections in there, so that so that it won't be as expensive or as wasteful to produce a part. So there's some tolerance types that we have to consider. Unilateral is unilateral is you have your base measurement and then your max to 0, or it could be your 0 to your minimum, and then your bilateral is your base plus or minus the tolerance. So you could think of it as like unilateral. You're only having one tolerance for a top or a bottom, but your bilateral you are having both. Limits, it's just you're just only putting your limits are your max and minimum. And so tolerances are best used with baseline dimensioning, because if you're doing chain dimensioning, tolerances can build up, and that won't end well. So I did not put this on the slides, but I'm just gonna say it outright. So when you're doing tolerances with imperial or metric system dimensioning, it's really different. So you don't want to have a bunch of decimals when you are using the imperial system, or inches or feet or whatnot. That's only useful in your metric system. So just a heads up. So with your fits, there are 3 types that we went over, which is transition, clearance, and interference. Transition is basically like you're allowing this part to move. Clearance is just like you have enough space for other stuff to move. And then interference is kind of like interference is just you're basically locking it in, and and you're not trying to move. And then we have some more vocabulary here. So clearance is the distance between 2 parts. Your tolerance is amount that 2 or more parts can overlap, and your allowance is your space between your max limit and your max limit of shaft in your hole. Or yeah. Okay, so another way that we can do tolerancing is through feature control frames. So feature control frames, they detail the part's relation, shape, tolerance zone, and feature reference. So our symbols here, we are gonna have to remember these symbols, because I'm certain that we're gonna be using these on the exam. So we have our forms, which is straightness, flatness, and circularity, and our orientation, angularity, perpendicularity, and parallelism. Location, position, concentricity, and symmetry. All these are kind of self-explanatory. Profile and line profile and surface profile. So line profile is just basically like what is this line reference to another feature? Your total, and then your surface profile is just basically what is what is the is basically like a combination of a bunch of different factors. Can't read it off at the top of my head right now. I'm sorry. If you can post it in chat, that'd be really useful. But yeah. But okay, so run out. So circular runout is basically just circularity of a feature. It's not caring about uh, sing, you're only caring about circularity. You're not thinking like, is this entire thing a straight cylinder? It's not. So, what's going on in the chat right now? Flatness and straightness.
I just want to add, because I noticed it not on the chart there, but just want to add under circularity, there should also be cylindricity, which is basically circularity, but for a cylinder. And the symbol for that is a circle with like 2 slashes on either end of it. Yeah. Also, the difference between straightness and flatness is how straight a line is versus like how flat the overall surface is.
Yeah, what's this? How flat a plane versus how straight or line this is. Oh, okay.
Yeah.
He already got it. Okay, okay. Anything else before we move on? Oh, excuse me. We're almost done, folks. Just give it a little bit. Okay, well, while you're typing your question, we'll continue on. So, your feature control frame, you're gonna start with your geometric characteristic symbol, which are the symbols on here, which is your first, and then you have your stated tolerance, and then maybe a modifier. So if the most common modifier that we see is maximum, is maximal material condition, but there's also L, which is least material condition. So this is just like an extra modifier depending on the material. And then sometimes you will see the diameter symbol here. Basically, that's just to say like this is a dimension for a hole or a slot or whatnot. And then you have your datums, which we'll go over later. But so like the last part is going to be for your references, which are datums that we're going to go over really quickly. What is this? Are we going to practice and review for part B? That's a little difficult for this. One way that I could say the best way to practice for part B is to just, I would say to just draw some certain parts that you're going to be doing. So like for an example, you can go onto the Gestalt, or the what is it, the the review page that we got. Or yeah, you can go into the textbook and you can actually just start drawing some of the parts that are going to be on there. And that will help in like, okay, what is the difference between isometric and oblique? How do you mirror something? What is the cross section of something and whatnot? Okay. There we go. Yeah, there we go. We can move on to the next slide. Okay, so datums. What the heck are datums? Essentially, they're basically reference points for when quality checks are being performed. So you can think of datums as like a surface for where the part rests and where it's being checked. So as an example, right? In this picture, you could see that datum A is leading towards the bottom surface. So it's going to be constrained on a flat surface. And let's just say like datum B is like the side, and then datum C is the top. So essentially, it's going to be constrained within that certain area. So it's going to be the part is going to be sitting on a flat surface, and then another on a horizontal surface, and another top surface, which will constrain it, and that will allow some kind of machine to do some quality checks.
All right, so we're going to move on to design analysis now. And so basically the two main things with design analysis are your properties of mass and FEA, or finite element analysis. So your mass properties are your center of mass, which is basically where you could where your part would be perfectly balanced in 3D space. Surface area, pretty sure know what that is, but the amount of area that you could see from the external of the object. Volume, how much space the part takes up. Density, can't say how dense, but like density is basically like how condensed the part is inside the space that it takes up. And then moments of inertia. Moving on to finite element analysis, also known as FEA. Basically, it divides parts into small subsections called meshes. These are usually geometric shapes, such as triangles, squares, or usually any other polygon. And individually, they calculate stress. And there's different types of stress, such as mechanical, thermal, air, liquid pressure, and conductivity. However, constraints must be added before applying forces.
give me a second. I need to take another quick swig. All this talking is making my mouth dry. Okay, our last one that we should be knowing that we should know is formatting our drawings. So we want to present our drawings as the best as our best of our ability and make sure that it's clear and make sure that like people can actually read it. Otherwise, your manufacturer or your boss is going to be like, "What the hell am I looking at?" Essentially. So, there are multiple sizes here, which is labeled as A, B, C, D, E, as we went through this in all of our CAD assignments. So the size increases in in alphabetical order, and there's also numerics, which will also detail the size. All right, so our borders is where the boundaries for all our tables and for all of our tables and drawings. They also include our grid markers. And then for our title blocks are going to include the metrics that we're going to be using, the company name, designer name, our scale for the drawing, tolerance, material, and approval signatures. And then our secondary title block is going to include design update logs. So basically, like who made revisions to this design, and how did they, and then when did they do it? So as you could see from the example that we put on this slide, all notes, drawings, and tables must be within the borders. Don't clump up dimensions or tables together. If you clump too many into one area, it's going to be hella cluttered, and it's going to be very confusing to read. So you wanted to make it as clear as possible, but don't have like a lot of space in your drawings because that's just going to be redundant. So if you have a drawing that's just way too big to put on a sheet, you might want to change your file. You might want to change your sheet size. Or again, if the drawing is too small, you want to make it bigger. So essentially, you want to have a balance of size so that other people can read it. So if you can read it like just fine, then that means that others can read it as well too. So when it comes to larger assemblies, you might have to do multiple sheets because where it's not just a singular part. You sometimes a customary part might have to be manufactured. So it's best to have multiple drawings for sub assemblies or even smaller parts. Okay, for assembly drawings. So as stated before, assembly drawings are how we're going to be putting all of our assemblies onto paper or another kind of medium. So, one moment, just eyes are dry. So again, as stated before, when it comes to assembly drawings, it's best that you have multiple sheets for parts that are customary or like just for better visual representation. So there's three kinds that we have to know. Outline assembly drawings. So it's kind of like exploded drawings, but they have like markers and pointers to where the part is going to be assembled. An exploded part or an exploded assembly is self-explanatory, as you're essentially taking the part and you're just showing like, oh, what every part is going to look like prior to assembly. And then a section assembly is the completed part, is the completed assembly. But instead of like having every piece like disassembled, you're actually just only like cutting the full assembly to look at the individual components on the where they're supposed to be. And I think that pretty much covers it. So if you have any questions, please put it in the chat. I hope that this has helped you a lot. And yeah, good luck on finals, everyone.
Round of applause, everybody. Thank you very much, Santa.
So,
just definition.
parameters are not necessarily dimensions. So if I go back here, parameters are, let's see, should be back
Try
here.
session after files. Nah, dog.
So parameters are attributes of features that can be modified. So dimensions are a part of it, but geometric relationships are also parameter. So again, the main thing for parameters is just anything that can be modified.
Right. So like you have like your constraints or some like or again dimensions. So basically anything that can change the part that's considered a parameter.
Alrighty, thank you.
Yeah, no problem.
Yep.
What is the difference between extrusions and protrusions again? So extrusions you are it's the process of making a 2D sketch into a 3D object. So say like you have a square, right? And you want to turn it into a cube. You would extrude that square to make it into a cube. Now for protrusions, you're creating a feature. So you have a cube and say you want to put a cylinder on it. You would then you would draw a circle and then you would extrude that on and that will make a protrusion. So a protrusion is basically an extrusion on a 3D object. Just think of that. Yeah, no problem.
All right. Are there any other questions? Yeah. So just to recap it, like Santana said, basically extrusions cause protrusions in most cases.
Oh, by the way, if any of you have arrived late, that's totally fine. We are going to be posting the slides and also a recording of this session on the chat. So just a heads up.
All right. Don't see anyone typing. I think that's it. I'm going to cut the recording.
All right, cool.